Hello everyone, welcome to Materials Care webinar today. Today, I'd like to give a talk about optical property calculations. This presentation will be start from brief introduction to the optical process, and then I will show you how to calculate optical property calculation on Materials Care. So to better understand the optical process, we'd better to start with concept of light. What is light? We couldn't live without light. Generally, light is defined in physics by all kinds of electromagnetic waves. Also, in quantum mechanics, light is considered as not only wave, but also particles. This is called duality of light. As you may know, the energy of an electromagnetic wave is quantized to electron or photon. Basic unit of electromagnetic wave energy quanta we call photon. Right? Look at this figure. Light can be separated by gamma or X-ray, and also ultraviolet and visible area, infrared, and microwave, and some long radio waves, right here. So UV, VLIL, microwaves, LEDIM is follow up from the here to here. Okay. So according to the Planck-Einstein relations, which is actually originated from the black body radiations, photon energy can be expressed by the HANU, like this, E equals HANU, and where the E is photon energy, Ha is a Planck constant, and Nu is the frequency. All right. It states that photon energy is proportional to its Nu. It can be also expressed by this equation, E equals Hc over lambda, because photon is always follow the speed of light. In here, lambda is wavelength and c is the speed of light. Optical properties are determined by interactions between electromagnetic wave and materials. The same concept as above apply whether it is experimental or calculations. So we should analyze the kind of reaction or interaction between them. So I'll explain two types of materials, metal and non-metal. So I'll focus on the non-metal case, especially semiconductor today. How can we see the color of metal? Some metal, we assume that this is metal. Okay. We can see the color of metal, right? It's quite simple. In the metal surface or near surface, most of incident light is reflected. This is the incident light. So it's arrive the surface. Most of light is coming through the here. Okay. This is usually general reflectance of metals around more than 90%. Okay. So most of it is reflected because the absorption of light occurring at the highest energy level, and photons are emitted directly from the high energy level to low energy levels. Remember that incident light arrives on the surface of metal, the free electron in the metal which have high energy level to low energy level. This is absorption and emission on the metal. The high energy level to the low energy level. You should remember this. In case of the semiconductors are a little bit different. We should fully consider many things such as transmission, absorption, reflection, refraction, diffraction, and scattering phenomena. I found a nice figure to explain this kind of phenomena here, this figure. For example, transmission in this case, and absorption in this case. It looks similar phenomenon, but it's quite different. Transmission occurs when incident photon energy is smaller than band gap to target material. We can look and see here, and the photon energy is smaller than band gap, and absorption is occurring at the photon energy is equal or larger or equal to band gap energy. So how about reflection? We know the reflection or refraction, diffraction, scattering of the what is this one? So reflection is light traveling on opposite direction on the surface or material. And refraction is change the speed of through which medium pass through the another substance. And diffraction in here when the light passes through some slit here. And scattering is this one. The light is propagating in various directions on the surface of the medium, like this incident here, and like this. This is scattering. Okay. This is the interaction between semiconductor and light. As you know, the most important features of semiconductor, it has a band gap. Band can be defined by difference between valence band of electrons and conduction band. So we can calculate the band gap like this equation, Eg equal conduction band minimum, difference valence band maximum. So I showed the band gap of some semiconductor are shown in this table. One of the most famous semiconductor, silicon, has 1.1 eV at room temperature. And germanium, in this case, it has 0.7 eV at room temperature. Here, we should remember one thing. In density functional theory calculation, except Hartree-Fock calculation or GW calculation, which are very heavy and accurate calculation, experimental and calculated value do not match always. Because there are many reasons for causing these differences, but one of them is the potentials. Anyway, let's get back to the band gap. All right, this figure shows the electronic band structure of germanium, this one, along with the high symmetry point L and gamma and X. So depending on the crystal type, high symmetry points are defined differently. Yes. And you can see the small figure in here. So this is the germanium, first brilliant zone of germanium. And there are so many high symmetry points in here. And high symmetry points are defined differently. Okay. So germanium is a face-centered cubic structure. So first brilliant zone looks like this. Okay. So you can see the gamma is a zone center, and L is here, and X is here. So in this figure, plot L to gamma and gamma to X, right? So this is this figure is kind of things. So germanium has an indirect band gap of 0.9 eV. The valence band is located on the gamma, and conduction band minimum is located at alpha. Look at this figure here. This is a billion zone center gamma, and this is the L point of the conduction band minimum here. So this is the indirect band gap. So value is 0.9. Okay. However, on the billion zone center, there is a 1.1 band gap is shown. This is here, right? This value is 1.1. It's only difference from the 150 milli eV. So many researchers try to indirect to direct band gap material through the doping, also getting stress on the sample and so on. In semiconductor, the dominant interactions are absorption and emission, which occurs the ultraviolet and visible light to the materials. Ultraviolet has 10 to 400 nanometer of wavelengths, and visual light have 380 to 740 nanometer of wavelengths. And incident phonon energy is larger than band gap. Electrons are excited inside the target materials. So inside the beam here, and some electron inside the material, there's gonna be some excitation and then going through the here. So excited electron, like for this one or this one or this one, is tended to return to the ground states. This energy difference will be released as a light or thermal energy. Okay, this is actually delta E. So one importance this can be achieved here. Assume that we have A material and B, C. Or if it has all material have different band gap, okay? Like E, G1, E, G2, and E, G3, for example. So what if we can measure this energy difference like this one for the A, B, and C? What can we get from here? So we can clarify the A and B, C through this energy, okay? This feature is very important concept on the optical process. What is reflectance, transmittance, and absorbance? Reflectance can be expressed by the here equal IL over I0 with IL is this one, incident irradiance, and I0 is incident irradiance, and also IL is reflected irradiance. All right. So reflectance L can be defined by IL and I0. All right. So typical unit is watt per square centimeters. So transmittance T is defined by the IT and IO. And IO is, I0 is already, I mentioned the incident irradiance, and IT is the kind of transmitted irradiance, right? So ratio between IT and IO can be defined transmittance. So according to the energy conversation, T plus L should be 1. So anyone want to exact value of intensity of absorbed light energy directly, but it is not possible. However, instead of this, absorbed intensity can be calculated by as follows. Here, I know the transmittance here, and then of course we know the absorbance, all right? So finally, using this one and this one, we can get absorbed intensity here. So absorbance A can be defined by as a function of transmittance T. It can be minus log 10 T. Absorbance is related on the transmittance, all right? So each optical properties can be measured in experiment directly. First of all, reflectance. IR over I0 details are already I mentioned previous slide. And second is refractive index and omega. This can be defined by ratio of speed of light in vacuum and speed of light in medium. Last one is extinction coefficient K omega. K is a function of frequency. It describes attenuated light when passing through the medium. It's also called mass attenuated coefficient, and this is imaginary parts of dielectric function. So this part, can be E1 plus I plus 2, right? So this part is extinction coefficient. I will explain on next slide. This is most important part today. When you finish this webinar, I will teach you how to calculate optical properties in here, in material scale. So those properties are dielectric function, refractive index, and absorption coefficient. After finish this webinar, you can calculate dielectric function and refractive index, absorption coefficient. So dielectric function describe the linear relation between electrical displacement and the macroscopic electric field. So here, we usually use the epsilon. So the epsilon here. So dielectric function can be expressed by the complex. So E1 is the real part of dielectric function, and E2 is the imaginary part of dielectric function. Usually, dielectric function plot as a function of photon energy here. So this figure shows the dielectric function evolution as a function of photon energy. This can be achieved very easily on material scale. So by definition, refractive index and omega and extinction coefficient k omega are related to the dielectric function epsilon omega by this equation, this relation. So square root epsilon omega equal to the, it can be expressed by the complex refractive index. So, and W is the real part of complex refractive index, and K omega is the imaginary part of complex refractive index. So actually in K omega we call extinction coefficient. I want to explain more details about times go fast, so please refer to the solid-state physics by Optical or Ashcroft Momin or some other nice book. The last one is absorption coefficient alpha. This is quite important features in the solar cell application and other optical applications. This is the reciprocal of the depth of penetration of radiation into the bulk solid, commonly inverse centimeter units used. Okay, so in here, like this, so alpha as a function of omega can be calculated from the extinction coefficient k omega, right? And divide by speed of light and times 4 pi, you can calculate the absorption coefficient alpha. This figure is also came from the material scale and optical properties calculated module here. So you can check the absorption coefficient as a function of wavelength, right? If you want to more details, please refer to open research page on material scale. Research material scale try to allow users to easily calculate the various properties of materials with very reasonable price. So today I mentioned optical properties and optical process. So dielectric function epsilon as a function of omega can be written by this. And then extinction coefficient relation between the dielectric function can be expressed by the complex refractive index. Finally, we can get an absorption coefficient alpha as a function of omega by using also extinction coefficient and speed of light. And more practically, if you want to calculate the real part of the refractive index and extinction coefficient, you can directly use this equation, right? This is, I already mentioned E1 and E equal is the function of dielectric function, right? So you can calculate the dielectric function. So you can also calculate the refractive index and extinction coefficient also. So our brief introduction of optical properties then. Next part will be tutorial session. Okay, I prepared two kind of things, but I only show the silicon case and gallium arsenide case is your homework. So I show you how to calculate silicon, and then you can follow up the gallium arsenide or silicon. So I'll give you a few seconds or a few minutes for the tutorial session. All right, so please open your browser, okay? We recommend Chrome or Safari. And then go to the MatSQ.com and then log in and click the work page. And please wait here, right? And also we prepare some how to calculate the optical property as a document. We are start from the modeling, okay? Exactly silicon, okay? We are going to prepare silicon for the optical property calculation. And first part, we are going to the relaxation. And second part is when you finish the relaxation, we perform the NSCF calculation. Okay, This is step 1. This is step 2. And when you finish the 1 and 2, finally you can get optical properties by using the optical property module. Okay, it's quite simple. All right, let's start. This is the materialscale.com or just press MatSQ.com. Okay, and you can go here and sign in. Okay, so please click the new work. Okay, so in here today, we are going to simulate the optical property of silicon. So press preset modeling and preset here, and then select the silicon conventional cell. Okay, make generate. Okay, a second to make the conventional silicon. As you may know, the silicon consists of 8 atoms in the cubic cell, but in DFT calculation, we do not use the conventional cell. So we are going to change conventional cell to primitive, okay? So press cell, and then press primitive, okay? This function will be find the primitive cell of the system. So in this case, silicon have 2 atoms in this cell. This is the primitive cell of silicon. So next, you press simulation and DFT and general. Okay, press general and then connect with the structure builder. This is the module connection. So you load the Quantum Express module, and Quantum Express module need the structure, right? So we should connect together. So click the structure builder, and this module is connected. So you can see the sky blue. It means connect with the Quantum Espresso. So you can see the many options in here. For today, we are going to relaxation for the optical properties. So you select the data to get you should change optical property. Okay. And precision, I want a little bit accurate calculation. So press high. Okay. And module type is the silicon is bulk. So just let them the bulk. And I will the optimization. So, right. So this is ionic optimization is only ions is gonna be optimized. Today I want to optimize ionic and cell together, so I'm gonna select ionic plus cell optimization. So if you select the optical properties, it automatically change stop potential. This is the non-conserving stop potential. In the Quantum Espresso, optical properties only provide for the non-conserving stop potential, okay? And also, if you want to calculate the optical properties on Quantum Espresso, you should turn on the no inversion symmetry, no symmetry option should be true. It means we do not consider the symmetry or inversion symmetry, okay? So our setup is done. You press the job name is silicon or relaxation. Okay, right? It doesn't matter if you want AAA or BBB, CCC, it doesn't matter. It's just the job name, okay? And press the job. So when you submit the job, you can see that this gonna change it to 1, okay? This is job name. This is a type of calculations, and this is the server for in the cloud, and this is the elapsed time. This is the payment, and this is status. Okay, so this status is preparation for the Amazon Web Service. So I wish to waiting for the few minutes. It takes a few minutes, so I want to introduce more features in the MatSQ here. And sorry, this is work. So actually, some of you guys interested in some special system, but it's actually very hard to get a structure from the website or some database. So we prefer the open database for the structure searching. For example, I'm interested in MOS2. Okay, so press MOS2 and search. Okay, so it's basically, as you may know, these of things. So MP is a materials project, right? So material projects, there are many crystal information are included. So if you want to use the MOS2, so you look like this. Okay, it's very easy. Otherwise, you can manually edit some crystal, but please refer to the modeling simulation on Material Scale YouTube. Okay. And you see this crystal, and this is MOS2 is a very famous transition metal dichalcogenide, and it has a very nice features like electronic or thermally. There are some very nice features. So there is very famous structures. So if you want to, if you modify some of these, I want to show how to clone this structure. Okay, press clone, cell and clone, and I want to more layers for this one, and this is gonna be changed to, okay, it's gonna be changed many layers, maybe 8 layers over here. 1, 2, 3, 4, 5, 6, 8, 7, 8. 8 layer MOS2 is generated, but I don't want more layer. I want to show this structure exactly. So I want to change this direction. Okay. And 3 times. Actually, this is MOS2 structures here. This is the actually 2D materials for the transition metal dichalcogenide. So one monolayer. Actually, this is bulk form, and usually MOS2 have a single layer. MOS2 is very famous for the good electronic structures or like a conductivity of them. So many of the researchers study for this material. So if you want to get some vacuum for the isolate system, press vacuum, and usually 15, right? 15 angstrom for the C directions, and apply here. Okay. So vacuum is added. So this system is from the bulk to the isolate system. So now this is the isolate system, not anymore bulk. Okay, and you can also clip or merge, or I already mentioned primitive cell or conventional cell convergence. So if you want to change it, like alpha, beta, gamma equals 90 degree, you press conventional. And if you want to find the primitive structure, you can press primitive button. So this is done. Actually, you can press the some button. It's not anymore. Because it's finished. So press the update status. You can find the successfully finished. Okay. So relaxation is done. But I want to check this structure is properly relaxed. So I want to I want to show one more things. So I want to see the compare structure. Okay. Press structure and connect to the relax module, right? Quantum espresso module, and press here. And then I want initial structure here, and press here, and then also press quantum espresso and press final. Okay, so this is what is different from this and this one. Okay, so you can see how to change the cell. Okay, cell vector A gonna be changed this amount, cell vector B gonna be changed this amount, cell vector C gonna be changed this amount. Okay, and if you want to check the atom differences, so this is delta, like first atoms. If you on mouse in here, you can check which atom is this one. Okay, show this one, yellow to brown, right? Yellow to brown, and this atom is yellow to brown. Okay, so there is how to check the method to the relaxation after relaxation. Okay, just click here, and then after that I'm gonna be calculate the NSCF calculation. Okay, so press simulation and press general. So in here, you can connect two modules. This one is relaxation calculation. This one is initial calculation, right? So you should select this one because we already get a relaxed structure. So NSCF needs a very stable structure, right? So you press quantum espresso here, okay? So when you select the quantum espresso, in this module automatically generate the two post-process. One of those are EPS calculation. One of those is joint density of state calculation, automatically generated. And this one is type is automatically optical properties with NSCF calculation. Other parameters are all set based on the before relaxation calculation. Okay, so I only change the grade. Okay, 16, 16, and 16. All right, quite simple. And the name is silicon NSCF calculation. Okay, and then start job. So we also, you can check this one. So 19 second, 20 second, right? So this state is also prepared. Okay, so just let them the calculation. So I'm gonna be back to the tier scale. Okay, I explained till the vacuum, right? So finally, you can put some vacuum in your system, right? It can be also quite using the atom section. In here, if you want to add atom, add molecule, or some moving atoms and rotating atoms and change atoms, right? So I try add atoms, all right? So I'm gonna change this atom. This is actually mode should be select module are gonna be changed, and press S is select mode. Okay, this is select mode. Keyboard S, you press S. This is gonna be select mode. And if you want to rotation mode is all. So all is the rotation mode. S is selection mode. Okay. Get here. I want to change these atoms. Select atoms, and this is gonna be changed to the carbon. All right. So apply. Sorry, this is add atom. Sorry. One more strong. Is X, Y, G direction. Apply. So this is add atom. And how about add molecule? Okay. So I want to draw a molecule in here. So I draw some something H2, right? So in here, done. Okay. And some position I want to fill in here. Now that's the number of molecule, article 5. Okay, apply. All right, you can see the 5 molecule of H2. 1, 2, 3, 4, 1, 5. 1, 2, 3, 4. This is the periodic 5. All right, this is 5 H2 molecule is filled. For if you want to fill another way, like origin or center of selected atom, for example, selected 2 atoms, selected 2 atoms, and then fill, it's gonna be some molecule inside between this and these atoms here. Okay. So another things is move atoms. I select here, then press move or move, and then after pass through the periodic boundary condition, it's gonna be also applied. If rotated also same, maybe 10 degrees, and select this here, and automatically center the atom of atoms. Center of a selected atom is the automatically. So right, this 10 degree, 10 degree, 10 degree. Okay, right. This is rotation, and you also use the change. Okay, this one atom. Change to the selenite. Okay, apply. It's gonna be changed to selenite. Molybdenum, not anymore molybdenum disulfide. This is selenite, molybdenum selenite. Okay, diselenite. No. Okay, so some of you guys interested in some simulation modeling, please visit the MatSQ materials care and then use this very nice simulation structure builder for free. Okay, and one more thing, important thing is here. If you want to export this file, and press here and tools and download it here. And please select if you want to bus format or CIF or some ABINIT, or some of you guys want to maybe LAMS format, right? And some of you guys want to quantum espresso input format. We provide many kind of structure type in MatSQ. Okay, so pass it, and it's gonna be downloaded in here. I want to show one more thing. New structure builder, and then just drag and drop. All right, this structure. Great. Okay. So I get back to the original page to check for the update status. Press here, update status. It's gonna be disappeared. My calculation is successfully done. All right. So last stage, post-processing, so I add analyzer and optical properties. Click this one. Okay. Also asking for the connecting modules. There are one available module to connect, right? So you should press here. You can finally get dielectric function and joint density of straight. And I already teach you what is the refractive index, or real part and imaginary part. And finally, you can get a absorption coefficient. I think this is quite good image for all plot, but someone want to plot another tool like Python or Excel or something like that, you press CSV button to download this data, okay? Actually, this is the three data in here, X and Y and Z direction, all right? So this it has three data, but you know the silicon is the homogeneous. I mean the X, Y, Z direction is symmetric. So alpha X, alpha Y, and alpha G direction should be same. So this is the how to calculate the optical properties on MatSQ. Maybe it costs $3 for $2. I think it's very cheap. So please follow up my calculation today, tutorial calculation, and then upload for the open research here. Okay. When you finish the calculation, right here, this is save. This is MK, and it's MK for the optical properties for silicon webinar. Okay, save first, and press this to publish. Okay, this is gonna be more categories will be there, and I will show the quantum espresso title. And for the title is optical properties of silicon. Okay, and some thumbnail. I did not prepare something, but maybe some image here, okay? And then press the description. Actually, this is the iPad, so there's some problem with that. What description is webinar 2010 27, right? Okay, and press this button, and then it's gonna be released to the world. This is gonna be published later, and then save. Okay. Thumbnail. You should be upload some thumbnail and then press publish button. Okay. So please, do you have any question? Please leave the message our MatSQ channel on YouTube or MatSQ. Okay. Thank you so much, guys. Thanks. Bye bye. See you next.